Hey everyone, welcome back to Robotics. I hope you guys are doing well. Today we have our 23rd lecture on linear control. All right, so let's get started with a video. Now, we've seen this video before when we were talking about forward kinematics, but I want to revisit this video from the perspective of control. Within control, I'm thinking about the forces and the torques in my different robot joints, and I want to pick those forces and torques to make my robot move in whatever way it is I want my robot to move. So, for example, maybe I'm controlling my robot to reach a desired position or trace a reference trajectory. In today's lecture, I'm going to introduce control for robot arms. I'll talk about what is control and why we use it, and I'll also recap some of the basics of linear control as they apply to robot arms. All right, so let's get started with a serial robot arm. In our last few lectures, we've been talking about dynamics. And we realized that the dynamics of a serial robot arm tell us about the relationship between the forces and torques at its joints and the way that this arm moves in space. So if we think about this specific robot, we might imagine these different motors that are connected to these joints and how we could pick the currents and torques at these motors for tau 1 and tau 2 in order to make the robot move its end effector. So let's say that the robot's current joint position is theta. And I want the robot to reach a desired joint position, which I'm going to call theta underscore d. So given our dynamics, how do we control the joint torques tau in order to make the robot move to some desired position? Well, that's where control is going to come into play. So what is control? Controllers are designed to drive a dynamical system to a desired state. Just thinking back to that example, it could be moving the robot's joints to a reference or desired position. The way we implement control is usually with computers or microcontrollers that are connected to our robot arm. The controllers talk to the robot in real time. They input the error, or maybe the position of the different joints along my robot, and they output signals I'm sending to the robot like currents or joint torques that tell the robot how it should move in space. And when I say real time, I mean something like maybe even 1,000 times a second. The robot is inputting its position and then trying to pick new torques in order to reach that desired position or track a reference trajectory. Okay, so maybe let's look at an example so we can better understand this concept. So here I've got a robot with two different joints. And let's imagine I want to control this robot to move its end effector in a circle. So some basic questions. Would you want to pick a constant torque, or does your torque need to change over time? Would you use the same force or torque for each of these different joints, or would you want to have different controllers for each of these different elements? I think at first glance, the control problem looks really easy, but when you dig into it, you realize, all right, I'm going to have changing torques that might evolve over time and perhaps even different torques for different joints. So there are a few ways we try to solve this control problem in robotics. And one way we do this is through something called independent joint control. So the idea is we recognize that yes, my robot arm is an interconnected system of joints and links. And we know that, but what we're going to do is we're going to break this system down and treat each joint and link as a separate subsystem. So I'll think about my first joint, I'll try to derive a controller that's just for that joint. Then I'll think about my second joint and derive a controller that's just for that joint, and so on. The advantage to this approach is that because I'm breaking my overall robot into these different subsystems, each of these individual joints and links is really a linear time invariant system, and so I can apply classic linear control techniques to that subsystem. For example, I can use things like transfer functions, poles and zeros, or PID control for that individual joint. The disadvantage of independent joint control is that because I'm breaking this overall interconnected system into these individual joints, I'm missing out on the interplay between their motions. So the forces that come from the motion of one joint are going to be treated as disturbances to another joint within my robotic system. Maybe looking at this example, when I'm only trying to control this first joint, this second joint, as it moves, will also apply forces. And I'm just thinking about these forces as some sort of disturbance to my system instead of recognizing that, okay, these are actually interconnected mechanical systems. So it'll have pros and cons, and we'll cover some of those advantages as we move through independent joint control. Now let's zoom in on that first joint and just think about what it means to control it at a joint level. So here's that first joint and link of my robot arm. It's got the prismatic joint and the link attached to it. Let's model this as a mass damper, where M1 is the mass of the first link, and B1 is the corresponding damping that maybe comes from our motor that controls the link. Tau 1 is going to be my force or torque that I'm using to control that link. And again, this is what's coming from our actuator. So we get to pick what tau 1 is as a function of time. D1, that's going to be the disturbance that's applied to this link. Now, this one is out of my control. It could be caused by interactions with the environment or just the interaction of this link with the other links in my robot arm. So we've taken my overall robot, broken it up into individual links, and now we can model these links as linear time invariant systems, such as a mass damper. At this stage, we can start to think about how do we control one of these individual links. And this is going to go back to our classical concepts in linear control. You might remember that one of our ideas is closed loop control. And the idea here is that I'm going to develop a controller that chooses torques based on the difference between my desired position and my measured position. So let me show you what that means with this block diagram down here. I'll start off on the left. So over here, this is my reference. This would be the desired position that I want this specific joint to reach. Maybe it's a revolute joint, and so I want it to reach 45 degrees. All right, that's my desired position. The first thing I'm going to do is I'm going to compare my desired position to my measured position. So maybe I measure 40 degrees. I'll then send that error to my controller. Say, all right, I've got an error of 5 degrees. What torque should I send to my motor in order to correct this error? That's going to be the joint torque tau. And again, since we're using independent joint control, all of these are just scalars, right? So this will be the torque for one specific joint in my robot. Now I send this torque, that's what I control, but there's also these uncontrolled forces or torques that could come from either interactions with the environment or the movement of other links along my robot arm. And that's going to be D right here. That's out of my control. The combination of my controlled torque and this uncontrolled disturbance go into my dynamical system and cause it to move. We call this the plant. I'm going to use the letter G of S. And really, this is just a linear time invariant system, maybe like a mass damper or mass spring damper that captures the movement of this individual link. I get out its true position, theta. That's going to be the position of this specific link. And then I use a sensor to measure that position, which goes back into my feedback loop. So we can use this closed loop control process in order to choose the torques we want in real time that will fix any errors between the reference or our desired position and the measured position. Maybe it makes more sense if I show you that kind of applied to one of these robot arms. So let's look at the first joint of this robot. Now, if I just think about this joint, I've got some reference position. Again, let's say it's 45 degrees, and I use the encoder that's within this joint in order to measure the robot's true position. Let's say it's 40 degrees. So I've got a positive error of, let's say, 5 degrees. Then I go to my controller and I ask my controller, all right, I've got this measured error. What should I do? We could just simplify this down as something like, if I have an error that I'm below where I want to go, let's increase the torque for my motors. And if I'm beyond where I want to go, let's apply a negative torque to go backwards. Really simple, right? So maybe that could be our simplified controller right here. I choose those torques and I send them to my motor in order to control this joint of my robot arm. And then the idea is I will repeat this process. It'll all be in parallel, but I'll be using this process separately for each of the different joints of my robot. So I'll be solving this process once over here, again over here, and so on for my independent joint control. Okay, so a bit more review of some of the key terms we need to understand for these linear control systems. The first term I want to review is the plant. So the plant is a transfer function that captures your system dynamics. And again, we're thinking of just an independent joint right here. So those system dynamics could be things like mass damper or mass spring damper. Now, when we're using independent joint control, because each link has been simplified, they all become single input, single output, or SISO systems. Here's one example down here. So let's say if we model our robot's link as a mass damper, then the plant is what you see right here. 1 over ms squared plus bs. Now, this is the plant written in the Laplace domain, and it's a relationship between the input force and the output position. Okay, so another term is the sensor. And this is also going to be a transfer function in the Laplace domain that captures how we measure the joint position theta. So if my true joint position is theta of s, then we're measuring h of s times theta of s. Now, for a lot of the robots we're looking at, we have very accurate sensors to measure my joint position. I can use things like encoders. And so h of s often just reduces to 1 because I'm directly measuring the joint position. But it could be something else. And so we have this more generalized h of s here just to capture what a sensor could be. All right, so we've got our plant, we've got our sensor. Now we get to the exciting stuff. Let's talk about our controller. So the controller will also be a transfer function, and it's just capturing our control law. If C of S is the controller, then the torque we're sending to our motor is going to be that controller, C of S, times the error between my desired position and my measured position. Here are 3 very common controllers you might come across with independent joint control. I've got proportional control, proportional derivative control, and proportional integral control. Pretty much any combination of PID is valid here. As a reminder, in proportional control, I'm just acting based on the error in the current position. So I look at the difference between theta d and theta, see how far off they are, and act proportionally to that. So Kp here is just a gain. With proportional derivative control, I act based on the error in position and on the error in velocity. So Kp, same as before, that's acting based on the error in position. S, that's going to take a derivative, and then Kd is my derivative gain. So this will be a controller that considers, again, the error in position and the error in velocity. A proportional integral controller is similar. You call that a PI controller. And here I'm acting on the error in position and the error in position that's cumulative over time. So I'm integrating with 1 over s and then multiplying that by a gain Ki. All right, so again, these are some common controllers you might have for a independent joint control. Now, you might be wondering, okay, there's all these different options. How do I pick the right one? And that's one of the big arts of control, is trying to understand the right way to choose a controller to make sure your system's stable and has good performance. I'm going to talk more about that in the next lecture, but for now, I just want to introduce one final thing that will be useful for choosing those controllers. And that is the characteristic equation. So to determine which controller to use and how to tune its gains, we often rely on something called the characteristic equation. And this right here is going to be the characteristic equation for our standard robotic control systems. 1 plus CGH equals 0. And again, if H is 1, it's just 1 plus CG equals 0. More on this in the next lecture, but it's just an important term to keep in mind. Okay, and so that's kind of a recap of what is control and why we use it, as well as some of the basics of linear control as they apply to robot arms. To test your understanding of these concepts, I encourage you to go through the practice set. You can find it in the description or the pinned comment. The first page has the questions and the following pages have their solutions. Once you've done that, I encourage you to move on to the next lecture. And in this next lecture, we're going to start talking about how we choose a controller using this independent joint control method that is going to have stability and good performance. So I'll see you there.